In this video, I want to talk about higher dimensional analogs of the Mordell problem about finiteness of rational points on curves. So the higher dimensional versions of Mordell. Okay, and I'm just gonna come out the gate and just say it. So here's the conjecture. And this is due to Lang-Bombieri and Noguchi. And it says the following. It says that if x over q is a variety of general type, so this means that it's going to be hyperbolic in some sense. Then it says that the rational points are not Zariski dense in x of q alge. Okay, so this is the conjecture. It says that there's not very many points here. So in particular, this implies Falting's theorem, implies the Mordell-Lang problem, the Mordell problem. Of finiteness of rational points on curves of genus G. Curves x over q of the genus of x is bigger than or equal to 2. Why is this? Well, the Zariski closure, if it's not Zariski dense, says so then it can't be one-dimensional. So then it has to be zero-dimensional, and zero-dimensional things on curves are just going to be collections of points. And so that's the idea. So this is the quick thing. So this is a generalization of this fact. In order to do this, I need to explain these words general type. I've said this on the channel before. I'm just going to repeat it again, just for clarity. So, let me just start with. I'm going to start with this Iitaka dimension. So we can take D is going to be a divisor on X. Okay, so we're going to take a variety X. Okay, and then we can associate to every divisor here L. This is going to be a line bundle or invertible sheaf. And this thing is here, this is how we denote it sometimes, or O of D. Sometimes I omit the X. This is going to be the sheaf of rational functions on X with poles at worst D. So we have this variety here, this subvariety or divisor, or combination of varieties. And what this is saying is that you're going to take this thing, and on an open set, we're going to say that okay, we're going to allow some poles, but the poles are not going to be worse than this divisor, or the multiplicity of this divisor that we have here. And okay, and then for each one of these guys, so for every line bundle, or in this case this divisor here, we can associate a map. Okay, so there's an associated map, and it takes X, and it goes to the projective space of the global sections of this guy. Okay, so we take the global sections of this sheaf. So these are functions with poles, global functions with poles at worst here. So we take a point X, and so maybe this could be considered a C point or whatever you want, and it maps to we take the sections or bases for these, and we map them like so into this projective space here. So this depends on a choice of coordinates. I should say that this map is rational. It's not everywhere defined, and since it's associated to this divisor D, we sometimes write it with this phi subscript D. And so this thing here, this is the rational map. So this is the map associated to a divisor. Sometimes it doesn't exist, but when it does, this is what we do. So sometimes this may be empty, so this doesn't make sense. But in the case where it does make sense, this is the construction. Okay, so now we have this thing, and I can define the Iitaka dimension. So the definition here. So the Iitaka dimension, dimension of x with respect to d. And so I'm going to call this Iitaka d of x. So this is going to be the dimension of, okay, so then we're going to take this divisor and we're going to, dimension, and we're going to take its image under this, some iterate, or some multiple of d. So we're going to allow more and more poles along d. And then we're going to take n really large, and this thing actually stabilizes, and this is for n sufficiently divisible. So we need n to be divisible by lots of primes, divisible. Okay, and so this defines the Iitaka dimension. So it's the dimension of the image of this map. So we have this map here again, like this, and so we're actually going to take a multiple of d, and then eventually we're gonna have it be in the image here. Okay, so this is what the Iitaka dimension is, and let's say that let me give you now a definition. Another definition. So a divisor is big. D is big if the following holds. This Iitaka dimension of x is equal to the dimension of x. So that this thing here, this map doesn't collapse anything. So there's not really, the fibers of this thing are not positive dimensional. And so this is what we call divisor is big. So let me give you a fact. So a fact is that this D is big if and only if well the number of the dimension of the global sections on X of this divisor. So this is, I'm going to omit this, and this is going to denote the dimension of H0. Is going to be approximately t to the dimension of x. So there's going to be lots and lots of sections, and so this says that there are lots of independent global sections. Okay, and so in particular, I should say, if you're familiar with the notion of ample, ample implies big. Okay, so we have this, and so there's a certain special divisor which is going to allow us to define the Karar dimension. So there's this canonical divisor associated to x, and this is given by the vanishing of top wedge power differential form. So this is when x is smooth. And so we can, this is what's called the canonical divisor, and it actually depends on a choice of form here. Canonical divisor. The divisor class of this is canonical, in that there's no choice, and we're going to define another thing, the Karar dimension. This is the Karar dimension. And so this is going to be equal to the Iitaka dimension with respect to the canonical or pluricanonical embedding. Okay, so the pluricanonical map, or I shouldn't say embedding, the pluricanonical map is again this map when we have when we're using the canonical divisor. Okay, and so now we can finally explain what the statement means. It says that we say that X is general type. If the Karar dimension is equal to the dimension of X. I guess we should note that the dimensions always going to be the Iitaka dimensions are always going to be bounded by the dimension of X. Okay, so this is what we want here, and so that now let me give you a remark here. So if X is a curve, So we say that x x will be of general type if and only if the genus of x is bigger than or equal to 2. Okay, so this is, and then sometimes this is saying that the curve is hyperbolic. So this, when we put a metric on it, this will be true or positive. And there's a whole system of conjectures about equivalent formulations of this condition. There's this thing called Kobayashi hyperbolicity and these things. So I'm not going to get into that in this video. What I am going to do is I'm going to, now I guess we have this Lang-Bombieri-Noguchi conjecture, and it makes sense. So let me just flash it up here again. So now we have this Lang-Bombieri-Noguchi conjecture. So that being said, I'm going to end the video here. The next video, what I'm going to do is I'm going to go back over these things in the case of function fields and explain how to do kind of a geometric versions of these things. So thanks for watching. Bye.